Hey all, welcome back to another Robison rant. And yeah, let's keep going. So, we've finished off our RLC circuits, our series and parallel circuits, and how they respond to a sudden change in input. That's what the switch is supposed to represent. You go from one state to another state, and then we practiced a lot on how to use the before and after initial conditions to take our generic equation and tailor it to the problem that we were dealing with. So now we're going to do something not like that, but we're going to do something that's an extension of that to make our lives even easier. And so hopefully you'll see how, after we get through a couple of videos, how we could have maybe addressed that situation in a slightly faster manner. Okay? So, to give you an outline of where we need to go, and we'll do this in a series of several lectures, we need to return back to our ideas about the imaginary number, j, okay? And how Euler's relation, e to the j theta, can help us in doing more circuit analysis. So I introduced this originally because of the underdamped solution to our RLC circuits. And I gave that to you because I wanted you to see where the oscillatory nature actually comes out from the differential equation. We're going to return to this guy now because the Euler relation allows us to take a differential equation and turn it into an algebraic equation. And that's what I would like to start discussing today, and then we'll hit that again when we talk about impedances. Okay. So right now we're going to set up the mathematical background, then we'll get some practical application. And then the fun thing is that when we use this to turn differential equations, differential equations into algebraic ones, the advantage to doing that transformation, if you will, is that then we'll find that our matrix techniques again apply. The small penalty for that is that we're going to have to develop some ideas about complex analysis. Say complex analysis, or complex algebra if you prefer. In other words, how do we do algebra that contains complex numbers? So that's where we're going to go. After we finish that, that will then allow us to treat things like RLC circuits for alternating currents. So we're also going to be going into, in addition to developing this formalism, we are also going to now start dealing with AC currents. Okay? So not batteries, not constant potential supplies, but time-varying periodic potential supplies, or current supplies for that matter. The last thing is that we'll find that you don't have to necessarily have a periodic function that is a cosine, or a periodic signal that is a sine, or even a combination of both of those. Okay? You can do things, we'll find that you can do things like a square wave, or a triangular wave, or a sawtooth wave. I guess I got those backwards, but that's okay. Okay? You ready to join me on this adventure? Tally-ho. So, one of the things that I was thinking about, and I thought that this might be a good place to start, is just considering an old problem that you've probably remember from previous classes. And what I was thinking of was just having, this isn't a resistor, I was thinking having a spring attached to a wall and attached to a mass, m. And of course you have your spring k here, the spring constant. And if you take m and you displace it by some initial distance x naught, you should be able to write down an expression for the time varying position as a function of time. Okay. You got it? Yeah. Good. Uh-huh. And you say, well, how do I get that? Well, let's go back to Newton's second law. Newton's second law, which says that the net force, net, acting on an object of constant mass can be related to the mass of the object and the acceleration of the object. Now we're dealing with a 1D situation. And so I could say, okay, well, I'm just going to look at the x component here because I'm only moving in the x direction. And the force acting on the mass, if I do a point particle representation, a free body diagram, the net force is acting in the opposite direction. We've displaced it one way. The net force from the spring is going to be pulling it back. So in this case, the net force, I guess we could also say there's the normal force, Fn, and the gravitational force, Fg. Okay. But the net force in this case is the force of the spring force. So we could put on the left side of this equation the spring force, Hooke's law. And on the right-hand side, I'll go ahead and employ my dot notation to represent the time derivatives. And now you look at this and you say, wait a minute, Greg, I've seen this before. I'll write it slightly more suggestively. That is simply a second order differential equation with constant coefficients. We've been dealing with those. Right? In fact, you could probably even go further. We'll put it like this: x double dot plus 0x plus k over mx. And if you're doing this in a circuits class, you would say that this is an underdamped harmonic oscillator, right? You see that this term, this B term, and this C term, you're going to end up with a negative value in the square roots. If I considered, the characteristic equation, found values for r plus and minus, you'd get something like r plus minus equals j times the square root of k over m. All right? And this k over m is sometimes referred to as omega naught, both in a mechanical system as well as an electrical system, which was given the natural frequency of the oscillation. Pretty cool, huh? So the final answer here would be something like a cosine, I'll put omega, technically it's omega d, but because alpha is 0, I'll just put omega naught here. Omega naught t plus b sine of omega naught t. And then lastly, we could say, well, we have to apply our initial conditions. At time equals 0, the box is at a distance x naught from the equilibrium. And that's enough to tell us that B, or excuse me, A is equal to x naught. Could probably also get some sort of, probably need a time derivative as well, right? The idea that momentarily, right at time equals 0, you could say that x dot at time equals 0. How fast is it moving right when you let go? Yeah, it's 0, right? Right when you let go, that box is just momentarily stationary before it starts to move. So x dot is equal to 0, and you can convince yourself of this. This lets you say that b is equal to 0. So at the end of the day, we get that our time varying position of the box would be something like x naught cosine of omega naught t. Pretty cool, huh? Okay, so that's just kind of a refresher. Remember, hey, when you have a box on a spring, it oscillates back and forth. Okay. Now I want to think about, we have the position of the box, but I want to try to think about it in a slightly different manner. Okay? Now, and the reason for it is that it makes doing some of the other calculations a little bit easier. So when you have an oscillatory behavior, you can express it in a different manner. So we have this x of t equals x naught cosine of omega naught t. Okay. And what I mean by another manner is that this is, if you will, half of the expression for the motion around a unit circle. Right? Physically, we have a box going back and forth, and so we get that cosine pattern. But you could think of this as one part of a larger picture. Say for a moment, I were to do something like x, and I'll leave this one cryptically unlabeled for a moment. And what does this tell you? You have a distance of x naught and a distance of negative x naught. And in fact, I'll put 4 in here. I'll put x naught here, and I'll put x naught here. And you could think of this equation as simply giving you the projection on the x-axis of the unit circle. So I'll go ahead and draw in a circle here, and that's why I meant for it to have the same radius all the way around. But imagine for a second that you have an arrow. Okay. You have a blue arrow, and that blue arrow rotates around counterclockwise at a speed of omega naught. Can you come up with an expression giving the location of the tip of that arrow as time progresses? Yeah. Hopefully you say, yes, yeah, I can do that, right? The x position, if I'm thinking about x's like coordinate axes, the x position of that arrow would be given by cosine of omega naught t. So I'll put x over there. And the y position of that arrow would be given by x naught sine of omega t. And maybe I shouldn't say y position, I'll say the vertical coordinate. Starts out, it increases in time until it's purely vertical. It keeps going, it increases in time until it's again horizontal, vertical, horizontal, yada, yada, yada. And so it kind of sweeps around the circle. I guess for lack of a better term, we'll call this R. Okay. Okay, good, good. And notice now that when we were dealing with our Springboks situation, you could think of that as simply being the horizontal component of this arrow that's rotating. Now you probably say, well, how does that help me? Right? Notice if I pull that x naught out, I have this cosine of omega t, this sine of omega t. I'll put the 0 in for completeness, but we're gonna only do in 2D. So I'm only interested in 2D, so maybe I'll take that 0 out. Okay. Notice that I can write it like this. And the last coup de grace, okay, I've written it in a manner that keeps the horizontal separated from the vertical. Now we're used to thinking of this as two separate coordinates, right? X component and a Y component. Okay. Something like a Y. I don't want you to think about that because this is not dealing with spatial positions anymore. Okay. Right? The analogy of the box on the spring, it's not that it's actually moving in the Y direction, in the horizontal direction, in the vertical direction. Excuse me. Coffee. Okay. It's not that it's actually moving in this direction. This is a bookkeeping maneuver. We're adding in this extra sine of omega t for conceptualization purposes, but at the end of the day, we're going to need to remove that piece. So, for example, what I'm going for here is that thinking of that box on the spring, we could represent the position of the box as a function of time. What I could think of is thinking of it as the part of two pieces, what we would call the real part, and I could add into it this imaginary part, this part that is not real, this bookkeeping part. I am. Okay. And if I add it in at the front side and I do all my calculations, what you have to remember is that at the very end, I need to remove the imaginary piece back off. It's almost like you say, okay, I'm putting it in there right now. I know it shouldn't be there. And I'm going to use that imaginary number to keep track, bookkeeping, so that I don't get it mixed up with the piece that I actually care about. Then at the very end, since I know that I introduced something that had an imaginary number in it, if I identify the components, the pieces that have the imaginary number, and simply remove those back out, then I've got my final answer. Don't worry, we're going to work on this a little bit more. The advantage here, by introducing this imaginary thing, I can now represent the position as a function of time. And don't forget, this is not a physical coordinate. Okay? Y is not the way to think about this. Think of this as some imaginary direction. And what the advantage is now I can write this using Euler's relation as e to the j omega t. So if I were asked to do some sort of calculation with this, I have now, rather than using my cosines and sines, I have now made it easier to take derivatives and integrals. I've introduced this e to the jx, if you will, notation, which makes it easier to do the integrals, to do the differentiations. And again, we're going to have to get some practice at this to kind of see what's going on. Now, I've been a bit cryptic about what to label this vertical axis. Okay? Generally, we don't label it x and unlabeled. This is generally referred to as the real axis and the imaginary axis. Again, the piece that I care about, the real axis, and the piece that I've added in for mathematical convenience that I'll later have to take out. And your final solution at any point in time, again, you can think of this blue arrow as rotating. Your solution at any point in time, well, you would have to find out how far around the circle the blue arrow has rotated. That would be your omega naught times your specific time. And then the position of the object is simply taking the projection of that arrow back onto the real axis. So it's a very interesting way of thinking about periodic motion. Rather than it being this 1D back and forth kind of thing, you can think of it as this 2D rotation with the projection onto the real axis being the value you want. Okay. This plane is incidentally referred to as the complex plane. And it will work just as much, it'll work just as well for the physical position of an oscillating spring and a box, or, for example, current flowing through a circuit. Say it's oscillatory current flowing through a circuit. We can do the same kind of modeling. So that's the ease of the presentation. You can introduce this imaginary component to your oscillation, and then using Euler's relationship, make it easier to express algebraically, and that will help with the differential equations. There's a little bit more advantage to this. For example, the geometric advantage. No longer do I have to think about 1D, I can think about 2D. And all of the wonderful things that go along with that. For example, let's say that you have the imaginary plane and the real plane. Okay. And now we'll go into a little bit more details. Let's say I give you a vector. Okay. So now we're thinking vectors. Oh boy. Let's say I give you a vector that has a real component and an imaginary component. Just make it 1 and 1. Okay. First off, draw this vector. You got it? Yeah, good. Hopefully, so I'll go ahead and label my axes. Hopefully that's starting to ring bells of physical vectors. Right? Vectors that give you 3 positions in space. Here we have a vector that gives us, I shouldn't say 3 positions, that gives you 3 coordinates in space. Here we are thinking of a vector and it gives a coordinate in the real direction, 1, and a coordinate in the imaginary direction, 1. And so that vector in the complex plane would be pointing in this direction. Well, let me ask you this. What's the angle that that vector makes, and we'll say with respect to x-axis? What's that angle going to be? And on top of that, how do you find the angle? Yeah. So the angle is going to be 45 degrees, or pi over 4 radians. And how do you get that? Well, we could say the tangent, and this is why I say you can start using your geometric relationships. You could say the tangent of the angle is equal to, the y component of your vector divided by the x component. And you're just doing triangle stuff at this point. And the y component is 1, and the x component is 1. Don't forget, we're using this j, if you will. We're using that j to represent that we're going in the vertical direction here. And then, of course, you have the inverse tangent of 1, which is pi over 4. Oops, excuse me, I swapped the order there. What about the magnitude of this vector? What should I write down for the magnitude of this vector? And hopefully you see it again. Excuse me, frog in my throat. Hopefully you see it again. You take the x component squared plus the y component squared, and then you take the square root. Again, I'm sorry, I fell into that vernacular. I should say the real component squared plus the imaginary component squared, and take the square root. So all of that vector stuff that you have developed in previous classes will come into play here. Last thing, well, not last thing, but another thing to note. So I'm going to introduce another idea that comes along with this complex analysis. And it relates to finding the magnitude of a vector. Let's say for a moment that you don't want to actually have to graph the vector in order to find the magnitude. You say, okay, well, I know. I'll give you a second way of doing this. Okay? And the reason I'm going to give you the second way is sometimes it's not convenient to get all of the imaginary pieces on their own. Okay? Sometimes you have an expression and you don't want to have to get all the imaginary pieces into a single term and the real pieces into another term. There is another way of figuring out the magnitude that doesn't necessarily require you to get all of those real and imaginary pieces separated. Okay? And fancy math term, it's called the complex conjugate. Okay. What the complex conjugate is, and I wanted to keep it on this page, so I'm going to just write it down here on the bottom. Okay. If you, notation-wise, the complex conjugate is, you'll see, for example, I'll use R here, and you put an asterisk on it. Okay. From this, that's mathematically how we notate it. From the standpoint of what does it do, okay, a complex conjugate, anywhere where you see a j, an imaginary number, replace it with a negative j. So that's step one. So for example, if we are taking our R vector that I've written here, and I take a complex conjugate, I would write that as 1 minus j. Anywhere where you see a j in your expression, you can replace it with a negative j. And that idea is sometimes helpful for determining the magnitude of a vector, because we can then take this expression for the magnitude and write it, I guess I'll put it, we can take our expression for the magnitude and write it, the magnitude of the vector, the complex vector, is given by the complex conjugate dotted into the regular vector, and everything is square rooted. And you can check this on me. Okay? By doing the complex conjugate, you notice that you flip the sign in front of the imaginary number. Then when you do the FOIL, the first, outer, inners, last, you'll notice that the two terms containing the complex number will cancel each other out, right? Because you flip the sign. And because of that, you end up with a root 2 at the end. In fact, let's go ahead and do it real fast. 1 minus j times 1 plus j equals 1 minus j squared. And I'm sorry, I forgot the square root. And what do you notice? J squared is -1. Yeah. So that's how that whole kind of process works. Okay? You take the complex conjugate and you multiply it, you will always end up with a real number at the end. Okay? If you don't end up with a real number at the end, after taking the complex conjugate and multiplying the two quantities, something has gone terribly wrong for you. Okay? Okay. So I would encourage you, go ahead and think about that more. The problem probably about the two things that I want you to really make sure unlock in your brain, make sure you really have it down, is this idea of using the imaginary axis, this complex axis. Okay. Number one. So in some sense, you can just think of it as a different dimension. Okay. But it's not a spatial dimension. It's not a temporal dimension. It's just this other dimension. It's an imaginary one. And you can kind of think about the imaginary number as this bookkeeping maneuver. So you insert this extra piece to help you with oscillatory motion, to express it as a circular motion instead. You do all your problems, and at the very end, we're going to pull that piece back out and get rid of it. Okay? People do that, and what they'll do is they'll say, okay, I'm only going to take the real portion of my expression. So I think I'll stop there for right now. Of course, I've got a little editing, so it's a shorter video on the whole. But from the mathematical standpoint, it's a pretty deep idea. Okay, so go ahead, make sure that you have kind of an idea of what's going on there. Okay, and yeah, we'll keep going with our videos. So I think the next thing I'm going to talk about is impedances. Okay, so we're going to now start using this idea of Euler's relation to insert this extra piece, do our calculations, and then remove that piece. And we're going to start with some, if you will, simpler circuits. Okay. So I'll start off with something like an AC potential supply and connect it to a resistor. And what we want to figure out, like always, is getting an idea about the relationship between the potential, the applied potential, and the potential across the resistor, or the current through the resistor, if you will. That's basically the name of the game. Find a relationship between the potential and the currents. And we'll do that for a resistor. And we'll do it for a capacitor. And we'll do it for an inductor. And we're going to find out some pretty neat relationships if we go into this complex analysis. Okay? So stay tuned. That's the primer. Okay? Stay tuned. Thanks for your attention. I'll see you next time.